Okay, this lecture we will start some new topics on the classical complex analysis materials. It will not be as a computation involved like last week, so life will be easier. So but of course the material is important. So argument, principle, and Runge's theorem. And so let's do some setup. If holomorphic function fz defined on an open neighborhood of A in C has a 0 of order k greater than 1 at A, then we can write f as z minus a to k's power times gz, and with ga non-vanishing. The point A is an isolated singularity for the logarithmic derivative. d dz log fz equals f prime z fz, and the principal part is given by k over z minus a. Okay, so let's first do some remark. Notice that log fz is not well defined on the neighborhood near 0 of f. So for example, a is 0, then so this is your domain, omega for instance. So in a neighborhood, log fz is not well defined because you have ambiguity. You cannot take log. You need to do some cutting. So usually when you do this cutting, but since the ambiguity is 2k pi I, that is to see the multiple values differ by 2k pi I. Therefore, if you want to eliminate the ambiguity, one way is do cutting, the other way is do derivative. So d log fz without the computation, must be well defined holomorphic function in yellow part. And you see here, you can see the difference between log function and the power function. Because power function, the ambiguity is not 2k pi I. It's changing from point to point. So even if you take a derivative, you still have ambiguity. That is, omega k, even if you take a derivative, you still have k omega k minus 1. So if k is not a integer, then you cannot define, the derivative is still not well defined in the full neighborhood. So that's a difference. Okay, now next, to get precise, principal part we just need to calculate. So probably a better way avoiding define log fz is you just view logarithmic derivative or logarithmic function as f prime divided by f, and plug in the formula. So f prime is z minus a to k's power divided by times gz, take derivative, divided by z minus a gz. Okay, then you have g prime z divided by gz plus k z minus a k minus 1 divided by z minus a k's power. So if you cancel out, this is k over z minus a. And this part is holomorphic. Okay, therefore, the logarithmic derivative or some holomorphic function has at worst simple poles. Next, we'll apply this observation. So let omega be a bounded open subset of C with piecewise smooth boundary. If Fz is holomorphic on an open neighborhood U of the topological closure omega bar or omega which is nowhere 0 on boundary omega, then the total number of Fz inside omega. So here we need to count the multiplicity with multiplicities counted is equal to 1 over 2 pi I integration partial omega f prime f dz equals to 1 over 2 pi I partial omega d log f. Okay, and if you draw a picture, that is, suppose you have domain omega, let's call this U, and then inside you have domain omega with piecewise boundary, so that you can define the line integral along the boundary. And probably you have several pieces, not only one. Okay, then Fz has some zeros inside it, not on the boundary by the assumption. A natural question is, how many 0 points do you have inside omega? Then the answer is the number is equivalent to the integral. Later on we will give some geometric explanation. Here we first prove this. It's just one line proof. So by residue theorem, the integral equals the summation of residue z equals a j, or the aj inside, and f prime over f. And we know that f prime over f has a pole if and only if f, so at a, if and only if fa equals 0. Okay, because f is a holomorphic function. Okay, and also because f prime over f can be written down as k over z minus a plus some holomorphic functions. Then this k corresponding to the, okay, so let me write f z equals z minus a k's power times h times g. Here you have, let's use g. Here you have h. So this k here corresponds to the k here. Okay, so by this formula, the expansion we know residue z equals a f prime over f is k, which is exactly the number of zeros at point A. Number zeros at z equals a. Okay, therefore you have a geometric interpretation for this part. This is summation of so the total numbers of zeros of f inside omega, and with multiplicity counted. So this means that if you have if f is z minus a to k's power times some holomorphic function which is non-vanishing at point A, then you have k zeros at point A. Okay, so this is a proof, and we can generalize it to meromorphic functions, but then we have a different interpretation of the residue. So omega is as above if f is a meromorphic function on U which has no zeros and no pole on the boundary, then the total number of zeros of f with multiplicity counted minus the number or poles. So here with orders counted inside omega is 1/2 pi integration partial omega f prime over f dz equals 1/2 pi integration partial omega d log f. So let's make one remark first. So before we said if f is a holomorphic function, then okay, if f is a holomorphic function, then we can draw the conclusion that f prime over f has principal part k over z minus a. So now, for our case, if f is a meromorphic function, then we can write z minus a to k's power gz. We also assume ga is different from 0, but k is an integer. Okay, by similar argument, we can show that the principal part of f prime divided by f is still k over z minus a, but now k might be negative. And what's the geometrical meaning for this k? So when k is positive, this is multiplicity of f at z equals a, and when k is negative, when k is negative, k is negative k. Okay, sorry, let me think about it. Yes, negative k is the order of f at z equals a. Okay, then let's carry out the proof. Proof is exactly similar. So when you do this integral, because of the assumption, the boundary f prime over f is continuous on the boundary, so you can use residue theorem. On the other side, you have residue z equals a, and aj, for example, f prime over f. And then the geometric meaning of this, you separate it into two parts. So first is the residue positive, f prime over f, and then plus where the residue is negative, bj z equals bj less than 0, or bj. Okay, then the first part is the total number, geometric meaning, total number of zeros with multiplicity counted. And then second term is negative number of total orders of the poles. Or probably here we give another interpretation. Probably it's easier. Aj is a 0 of f prime over f, bj is a pole. Oh, sorry, bj is a pole of f. So here is also f. Okay, then we are done. So when the boundary, next we give a geometric interpretation of the logarithmic derivative. When the boundary partial omega of omega is a single connected simple closed curve C, and now we just do the integration based on the definition of log f. So this is log f plus I, the argument f. And it's clear since C is closed, so log f, absolute value f, is a primitive of d log f, absolute value of f. So the immediately consequence is integration along closed loop C. This is zero. Okay, but then for the other part, what is this one? So this will be the 1/2 pi integration C d argument f. The argument integration argument f, let's see, it will be argument, for example, we fix a point. So let's call this point A. And then when you turn back, we call this point A hat. Although at the same point, but this A prime is traveled along the whole loop from A. So this will be A hat minus argument I will use different color, sorry. A hat F A hat minus argument F A. So what's the meaning? That is the change of the argument. Oh, sorry. Here I miss. Oh yes, it's okay. The change of the argument of f along C. And then the geometric interpretation. So the number of zeros inside omega minus the number of orders or poles inside omega is a change of argument. And let's look at one example to illustrate this idea. Suppose you just have a disk, and your f is z, which is exponential I theta. Okay, now you start from point A here. You go around. Eventually, you have A prime at the same point. Okay, then your theta from 0, pi over 2, pi, 3 pi over 2, and finally at 2 pi. So this is at point A hat. What is the change of argument? So the change of argument is 2 pi minus 0, which is 2 pi. Okay, and then here I missed. You have 1 over 2 pi here. We should normalize it. Therefore, we have the conclusion: the number of zeros minus the number of orders of poles inside omega, inside the disk actually, inside the disk is 1. And this is true because Fz is z. Okay, so this idea, if you put Fz equals z times z minus 1 and draw a circle with radius 2 centered at 0, you would have the same observation. Okay, then next, Roche's theorem. Let f be a meromorphic function on U contain the topological closure of omega. Let G be a small perturbation of F. That is to say, absolute value of, so small perturbation has a lot of meaning in different contexts, but in this theorem we only assume that the absolute value of G less than absolute value of F on the boundary omega. So this is the condition. Okay, then we have the conclusion. Summation of zeros of F minus summation poles of F with order counted equals the summation of zeros of F plus G minus summation poles of F plus G. So for the proof, the proof is a very classical, very typical deformation argument. You will meet this a lot if you learn further courses. For t between 0 and 1, fz plus tgz has no zeros and no poles on partial omega. Okay, then notice that for any fixed 0 less than t less than 1, the integral 1 over 2 pi I f prime z plus tg prime z divided by fz plus tgz dz along the boundary is always an integer because of the previous theorems. This integral has a geometrical meaning which counts numbers of zeros minus the numbers of poles. Okay, and now what do you have? Then you have, let's look at, you have map, so this is, let's call it gamma map from 0 to 1 and two integers, and t maps to the integral okay, and noted that also on the other hand it is clear that gamma is a continuous function on t in t, because you can look at the integrand. Integrand is a continuous function of t, and then you do the integration and the assumption the integrand is always good, then the whole integral is a continuous function in t. Then combine these two, what does that tell you? That tells you, so look at this. Suppose you have interval and you map it continuously to a bunch of discrete points. Continuous map. And by the property in Math 521 that you always map a connected set to a connected set. So that tells you the image gamma of 0, 1 consists a single point. So 1 over 2 pi I integration partial omega f prime z plus g prime z divided by fz plus gz dz equals 1 over 2 pi I integration f prime over f dz along partial omega. So we are done. This idea is very deep. Actually, it means that later on in your study of mathematics or physics, you will have a bunch of in-series phenomena which is invariant and topology, or it's called, in physics, it's called topological protected. So that means you change the topology a little bit, the quantity is not changed, or like topological field theory, whatever. So it's preserved and the change of topology. Not all the theorem like this. For example, conformal theory, it will change if you change the topology. Okay. Then we have an application. Proof of fundamental theory of calculus by Roche's theorem. So let fz equals a n z n is non-zero complex number, and gz equals the summation of the lower order terms. Take r large enough, then on the circle defined by z equals r, the norm of f is greater than norm of g. Then we have the conclusion plus g prime over f plus g dz equals partial cr f prime over f. And when r large enough, you conclude everything. So for this one, you have n. This is clear because for f is an times z to nth power, so you have nth root. So this is easy to compute. And then that tells you an zm plus am minus 1 zm minus 1 plus all the way to a0 a1 z plus a0 has n roots with multiplicity counted. Because it's polynomial, there's no pole. Okay, next, apply the Runge theorem. We can prove another interesting theorem due to Horowitz. So theorem Horowitz. So let omega be a connected open subset of C, and f and z be a sequence of holomorphic functions on omega, which approaches a non-constant holomorphic function fz uniformly on compact subsets of omega. The holomorphicity of fz comes from the fact that we proved before. You can either use Moreira's theorem to prove it, or use Cauchy-Riemann operator to prove it. We will not repeat here. Okay, so here, if each f and z is univalent, this is a notion univalent, but probably a more easy way to see it in modern language is Fn is injective, then then Fz is also univalent. So proof, we will prove by contradiction. So since Fz is, first we noted that since Fz is non-constant, then F prime z has discrete zero sets. That means the zeros of f prime is discrete. And assume that there exists points a1, a2 in omega such that fa1 equals fa2. So let's denote as b. Then we have the following. Expansion plus summation m equals kj infinity cmj m plus 1 z minus aj m plus 1. So here j is 1 and 2. Kj is greater than equal to 0. And cmj is different from 0. Okay, so the idea is we want to show that there exists fnz such that fn z equals b for two distinct points, which is a contradiction because we assume fn is univalent. So how to do this? So now what do you have? You have domain and you have a1, a2. Okay, they both take value b for function f. Okay, then we want to find a small circle such that the 2 points are separated by this 2 circles, and we want to show that fn has a 0 inside each circle. So let's call this a1n, a2n, such that a1n equals b, and here fa1, and here fa2 equals fa2n equals b. So that's our purpose. We want to find such point. Okay, since the circle are separated, so a1 are different from a2n. So how to do this? So that's the idea. So to do this, we just need to take care of the analysis part. Since exists r larger than 0 and epsilon larger than 0, such that fz minus b greater than or epsilon for z minus a j equals r, and z minus a2 equals r, where z minus a2 less than r intersection z minus a1 less than or equal to r is empty. So here r is greater than 0. That's exactly what we pictured here. The radius is r. We find small enough circles such that fz minus b on the boundary is different from 0. This can be done because of the assumption that So why this is true? Actually, we proved it before why this is. Because fz minus b equals z minus a to kj and times some holomorphic function such that gjz is different from 0. And you see, or from the isolation of the zeros, discreteness of the zeros, you can always do it. You first take r, then you take epsilon. First take r such that disks are disjoint. Then choose epsilon greater than 0. That's the correct order to do this procedure. And then there exists an integer, positive integer n such that fnz minus fz less than epsilon over 2 on z minus a1 less than or equal to r union z minus a2 less than or equal to r. This is because we assume that fn goes to f uniformly. Then fnz minus b can be written down as fz minus b plus fnz minus fz, and fnz minus fz absolute value is less than epsilon over 2 less than fz minus b on the boundary, and z minus a2 equals r. Okay, then by Runge's theorem, we can conclude that fmz minus b has a 0 in z minus a1 less than r, and a 0 in z minus a2 less than or equal to r. So which is a contradiction. So we are done. So that contradicts with our assumption that fn has two zeros. fa1 equals fab equals b. So the opposite is f is a univalent function. Okay, next we will talk about briefly the approximation by Runge method. Actually, we can spend a lot of time on this topic. For example, how to do the cutting, how to efficiently design the method or whatever, Runge method, approximation. But here we only give some rough idea and at least give you some concept. If you have interest, you can read some computational mathematics material. So suppose the simplest case, suppose you have power series z less than or equal to r less than also less capital R. It's convergent on the disk with I will say it like this. it's a convergent power series in the open disk, and then Fz can be approximated by polynomials uniformly on the closed disk. This is just the definition of power series. We know that we can dominate it by geometric series and show that it's uniformly convergent. Okay, now if we have a little bit more involved example, suppose you have a Runge series expansion on some annulus AK negative 1, sorry, zk plus k from 0 to infinity bk zk. Suppose this is convergent on the annulus, then we know that Fd can be approximated by rational functions uniformly on compact subsets of the annulus. So these two examples exhibit two kind of approximation. So first one, if you don't have topology, then you can use polynomials only. And second one, if you do have topology, probably polynomials are not enough. The best you can hope is rational functions. Okay, now we want to generalize it to arbitrary domain. So that's the usual order mathematician take. When you find some interesting special properties, people want to generalize it. Okay, but from my opinion, to generalize it is not that interesting. Even for the experts. And the best thing you can do, either both as a beginner and an expert, is to understand some key examples. So key examples, just like crystal. So out of the whole store, probably the store just famous for one crystal instead of a lot of cheap stuff. Okay, so just remember, keep some model in your mind. Okay, approximation for general domains beside disks and annulus. So first, let's do easy stuff, approximation by rational functions. Since we can use more functions, then the proof is easier. Suppose omega is any open subset of C and f is holomorphic function on omega. K is a compact subset of omega. So let U, the closure of the domain, is covered by the closure of some rectangles. such that U covers K. In other words, you want to find some rectangles whose interior. So let me find rectangles R1 to Rm whose interior covers the compact set K. Okay, then the conclusion is for Z in K, the Quotient integral formula yields that Fz equals 1 over 2 pi I integral along F c d c minus Z equals J from 1 to L 1 over 2 pi I integration Lj F c minus Z d c. Okay, so let's draw a picture. So this is your omega, and probably you have K here, and then you have a lot of blocks, rectangles, covers the compact set. So the compact set is everything inside. Okay, now since you have rectangles, so the boundary of where Lj is a horizontal interval or a vertical interval of the boundary partial union I from 1 to M. So what I denote Ri. So the boundary of the union of the rectangles must be a set of horizontal lines or vertical lines. Okay, then notice that each integral Lj F c minus Z d c can be approximated uniformly on K by Riemann sums of the form F c minus Z d c approximate equals to the Riemann sum F c K times the length delta c K over c K minus Z. And here, since the right hand side is a finite sum, c K is a constant, so finally it's a rational function. In Z, okay, since each term here can be approximated in the following way, we're done. I would like to make a remark about this. You will see from the proof that it's not necessary to take the rectangles. You can do something for K if the boundary of K is smooth. But if K is very bad, we have to take some better sets to cover it. Okay. If you have a better set to cover it, better means you have better boundary behaviors. It's either piecewise smooth or just smooth. Okay, then if you can do approximation on the larger set, of course you have approximation on the small set. Next, we will show that approximation by polynomials can be done only under some condition on topology. So notice that 1 over z cannot be approximate uniformly on the annulus by polynomials. So if you think about it, this is not so easy to prove, but although proof is one line, but probably you need to really understand the difference. That's called invariant. If you want to distinguish one mathematical fact from the other one, so how do you do that? Of course, you can exhausting all the possibilities and see they are different, but that's not so efficient, and sometimes it's not possible. So a quick way and efficient way is find some quantity, characterize the difference. So here, if you look at, so suppose polynomials fn uniformly converges to f equals 1 over z on the annulus, then you have the integral along the boundary converges to the integral of f along the boundary. So here C, let me denote this. So C is Z equals, for example, 3/2. Okay, then you have problem. That is, because Fn is polynomial, is 0, but this one is 1 by the 2 pi I, sorry, 2 pi I by the residue theorem. You cannot have this convergence. Okay, so that means if you want to approximate the set by polynomials, you need to have some topological condition on the set. So notice that it suffices for approximation by polynomials by the previous approximation for rational functions. It suffices to derive the approximation for 1 over c minus z for some c in the complement of the compact set. So the general setting is we want to approximate 1 over c minus z on K of by polynomials. Okay. So the easy case, if Xc is greater than the supremum or the magnitude of z inside K, then it's easy because you have the power series expansion. Okay, then we can show this by the previous argument for the unit disk. You have power series and you truncate it to deep order. Then you have a large polynomial approximate your function. Okay, then next general case. So let C be a smooth path in Kc starting with Xc and going out all the way infinitely. And in particular, joining Xc to some Xc star with the norm of Xc star is greater than supremum or norm of z for all z in K. And now let delta be the minimum of the difference between z and z prime. So where z is in K, z prime is in C. Then delta is positive. This is because you have K here. K is a compact set, and you fix a Xc. This is the point you want to in your formula, and then you connect it to some larger Xc star. Probably this is the origin. Okay, then you consider the distance between, actually this is a distance between two compact sets, C and K. So if the distance is 0, there must be a point in the intersection of C and K, which is a contradiction. Okay, therefore here, we always have delta bigger than 0. Okay, now we have the following claim. For any omega in C, if 1 over omega 0 minus z of z can be approximated by polynomials in Z uniformly on K, then for omega in C with omega minus omega 0 less than delta over 2, the function 1 over omega minus z of z can be approximated by polynomials in Z uniformly on K. So proof or claim. I will first give you proof, and then I will say more on this method. We still want to do the Taylor expansion of the reciprocal of linear function, and you have omega minus 0 times 1 over 1 minus omega over omega 0 minus z. Because of the assumption, we know that the following Taylor expansion, power series expansion, is allowable and also is uniformly for z in K, and for fixed capital N in fixed positive integer capital N, the function 1 over omega 0 minus z times summation from 0 to capital N, omega 0 minus capital N over omega 0 minus z to nth power, to small nth power. Sorry, this is omega. And you look at this, this is summation omega 0 minus omega to nth power 1 over omega 0 minus z to n plus 1's power. So this can be approximated uniformly by polynomials in Z on K. Because of the assumption 1 over omega 0 minus z can be approximated. Therefore, its product is also approximatable. Okay, then now choose omega 1 omega L in C between, sorry, not in capital C, mass BBC, is in the curve C between C and C star, such that omega 1 is C star and omega L is C, and the adjacent nodes are within distance delta over 2. So if you look at the picture, you just add more nodes inside it. So the distance is delta, and the difference between adjacent nodes is less than delta over 2. And then you're starting from C star, you can approximate the points one by one all the way down to C. So that's the idea. Okay, and remark, in this case, we actually show that every time you have some efficient improvement, actually you can have an efficient bound on how many times you need to do this bootstrap from C star to C. But sometimes you don't have this efficient way. Then what do you need to do? Every time you can only show, for example, omega is also omega 0 is good, and you know there exists small epsilon such that omega, so this epsilon depends on omega 0. For omega within the epsilon ball, omega is good. So then you might have the situation that starting from some omega, and then you go to some, or starting from omega 0, go to some points, but then you just stop some point. Here you have limit. You cannot go beyond this number, although your motivation is, your final goal is to achieve omega hat at this point. Okay, then you need to do one more step. That is, if you have omega 0, omega 1, omega n, such that omega n, you take a limit, this is called omega bar, then you can do the conclusion. If you can prove that the omega bar is also good, then you can also, by open close argument, you can also produce proof. In our case, we don't need to use the method in the remark, but then this method called openness plus closeness is very, very typical in PDE. Whenever you do a priori estimate, you want to show the existence of some solutions, the only thing you can do is do openness and closeness approximation. So openness usually means you need to solve the use the inverse function theorem. Closeness means you need to have some a priori estimates. Yeah, we will not study this in this course at all. But I would like to tell you, this is a typical method people developed for quite a long time. Okay, I will stop here. Next time we will talk about conformal mapping. Turn to another interesting topic.